conditions and the alerts going on here, but we are hopeful that tomorrow we can meet with him at the IAC if the conditions, if the storm has passed, and have a lot of interaction with him tomorrow morning. The speaker is Ian Rorderer from North Carolina University. We've been colleagues from many years ago. I met him when he was a grad student at UT Austin, and it's really nice how much work he's done since then, especially working on heavy metals, on neutron capture elements in stars. He's an expert on that topic, an expert spectroscopist on metal poor stars, on the halo, on nucleosynthesis. He got his bachelor in Indiana University, and then a master and his PhD at the University of Texas at Austin. He was also then a Carnegie Fellow at the Carnegie Observatories in Pasadena, and then later got a position as a research professor at the University of Michigan for quite a bit, for 10 years, before then moving to North Carolina at the physics department, where he's now. I mentioned already his expertise field, and well, that's precisely the topic he's gonna talk today. Welcome, Ian.
Thank you. It is a pleasure to be here. And just want to confirm everyone can see the screen.
Yeah, perfect.
Yeah, we could.
Okay, great. As I said, it is a pleasure to be here. And I look forward to meeting with some of you in person, hopefully tomorrow. Just as evidence that indeed I am actually here, I want to share this photo that I took this morning in Santa Cruz de Tenerife. It really is beautiful here, and I appreciate the invitation to join you. So, understanding the origin of the elements is one of the major challenges of modern astrophysics. And the big question that we want to answer is, how were the elements all across the periodic table made? And you can think of this as a story of how the three elements created in the Big Bang have been cycled and recycled through stars to create the rich diversity of elements that we find today in the solar system, in the sun, on the Earth, and throughout the cosmos. All of the structure in this diagram reflects the intertwined stories of cosmology and nuclear physics and astrophysics. And this all works because stars are born, they live, and then they die. And during their lifetimes, stars will fuse lighter elements into heavier ones. They release energy, and that is, of course, why stars shine. And then when a star dies, it returns some of those heavier elements back out into the interstellar medium, where they can be reincorporated into the next generation of stars. So as time passes, stars that are born later, toward the right on this diagram, have, on average, higher concentrations of heavier elements toward the top on this diagram. So what we'd like to do is to identify stars from those second and earliest generations of stars, where the elements in a particular star have an origin that is dominated by one prior nucleosynthesis event. And then we can use that stellar abundance pattern to constrain things like stellar models, nucleosynthesis models, and even some nuclear physics. So here's a schematic that I think can potentially be helpful to build some intuition about how all of this can work. So the abundances of elements that you observe in the universe can be thought of as some product of the nuclear properties and the physical conditions. If you know any two of these three, you can deduce the third. So, for example, if the nuclear data are known, you can derive the abundances in a suitable star or a well-mixed cloud of gas in the ISM or the IgM, and from that you can infer the conditions at the time of nucleosynthesis. So let's, as way of introduction here, talk through briefly each of these three pieces. And we'll start with the observations, the abundances. So the fundamental tools of my research are optical and ultraviolet spectroscopy of stars in the Milky Way and its neighboring satellite stellar systems. And then I use these data to derive stellar abundances. Here's an example. So the black line here shows a piece of the optical spectrum of a bright star, HD 222925. And you'll notice that all of the lines, all of the absorption lines, everything's an absorption line here, all of those lines of very heavy elements, which are the ones that I've listed in red, those are enhanced relative to the gray line, which is another star with otherwise similar properties. So using a measure of the line profile or the line strength, you can put that together with relevant atomic data, a model of the stellar atmosphere, and put that into a radiative transfer code, and you can derive the abundance. And that's just another way of saying the number density or the relative number density of each of these elements. So the next piece of the puzzle is the nuclear physics. And charged particle reactions, like proton captures, cannot overcome the high Coulomb barriers that are associated with heavy nuclei. But neutron capture reactions can. That's how you get the nuclear mass to increase. And then once the nucleus is in it, or once the neutron is in the nucleus, it can beta decay back towards stability to move you up the periodic table. And one kind of nucleosynthesis, one kind of neutron capture nucleosynthesis that I find interesting is the R process. The R process is one of the fundamental ways stars and stellar remnants produce the heaviest elements. And it uses a rapid burst of neutrons to overwhelm and grow the mass of existing nuclei. So the graph that you see here shows a chart of the nuclides. So that's a plot of the number of neutrons in the nucleus on the x-axis versus the number of protons in the nucleus on the y-axis. So all of the little black dots here, sort of near that one-to-one line, represent individual stable isotopes in the universe. And let's watch an animation of the R process as it runs along this chart of the nuclides. So you'll notice that the R process, represented by the little colored dots there, that flow of nuclei moves from light isotopes to heavy ones in only a fraction of a second. And then once that flow of neutrons shuts off, all of those heavy radioactive isotopes will decay back toward the stable ones. So the R process requires an explosive environment with very high neutron densities. The R process is the dominant source of the heavy elements that we find in the oldest stars. And then ancient R process events in other stars produced about half of the heavy elements that we find today in the sun and on the Earth. So the third and the final piece of the puzzle is a set of astrophysical sites. So we're looking here at one example, a site where the R process is known to occur. And this animation is showing you the merger of a pair of neutron stars. And this was the famous GW 1708-17 event that occurred, was detected 9 years ago now. And this was the first event where astronomers had a detection of both gravitational waves and electromagnetic radiation from the same event. And we get to this point right about here, we'll pause it, and I'll annotate sort of what's happening here. The part that I want to focus on is sort of that emerging donut or torus-shaped object in the center there. That outflow is called a kilonova, and the radiation emitted by that component is consistent with being powered by the ejecta of a few hundredths of a solar mass of freshly produced heavy elements. Those were all produced during the merger, and then they are returned back out into space where they can later be incorporated into subsequent generations of stars. So merging neutron stars are one confirmed side of the R process, but now that we have that association, that's actually raised more questions than it has answered. I mean, it's great to answer questions. It's even better to raise new ones. So how exactly are the elements from iron to uranium made? Can neutron star mergers do this alone, or do observations require that additional sites have contributed heavy elements in addition to the R process? And of course, I'm ignoring for now the other forms of neutron capture nucleosynthesis, the S process and the I process. Those are interesting in their own right. It's just not what I want to focus on today. So once we have an idea of the sites, you want to know something about the physical conditions of those sites. What's happening there? How extreme are they? What are the neutron densities? What are the entropies? What's happening? And in order to answer these questions, we're going to draw from a wide range of different fields, everything from stellar and galactic astrophysics to multi-messenger astrophysics, and of course, nuclear physics. And then once you understand the physics of these heavy elements, the physics of the R process, you can use that to inform your understanding of other things. For example, you can study stellar physics in the early universe. You can chemically tag the hierarchical assembly of our galaxy and local group of galaxies. You can assess the distribution of metals throughout the interstellar medium and the intergalactic medium. You can use this to understand the heat budgets, the impact of the radioactive actinide heavy isotopes on heat budgets of planets. And you can even potentially provide some novel constraints on nuclear physics models that you would not otherwise be able to get from experiments, for example, accelerator experiments. So this that we'll use to think about how we go about exploring the origin of the elements, at least for the next 30, 35 minutes or so. Who is doing this work? Well, a lot of people around the world, including some of you who are on the Zoom today. It's so great to have you with us. Here's sort of a slide of my little group of people at NC State University in the United States. Shivani Shah is a postdoc working in the group, working to connect stellar abundances to kilonova observations. Pranav Charvu is a graduate student working on the signatures of low metallicity stars that you might data. And then Zarina Husseini, Kate Casarella, Thomas Doughty are three undergraduates who've been in my group for a few years. There's a photo here of them shown where they presented their work in posters at a recent meeting of the American Astronomical Society. And then Cameron Lawrence is also another undergraduate who has very recently joined the group. I'm also a co-founder of a group called the R Process Alliance, and we are a collection of folks from the astrophysics and nuclear physics communities with an interest in solving the big questions related to the R process. And much of the work that I will show you today was done as part of the R Process Alliance. And anytime that's the case, you'll see the little logo pop up next to the reference at the bottom of the slide. Okay, so you cannot reproduce the R process under controlled conditions in a laboratory. It's just too extreme. Now, some useful but imperfect tests have been carried out here on Earth. The photo that you're looking at shows an aerial view of some of the craters that were excavated by subterranean nuclear explosions at a place called the Yucca Flats. This is in the Nevada test site in the western United States. It's on unceded land from the Western Shoshone tribal nation. But over the course of a few decades during the last century, 23 tests among the thousand some that were conducted here, 23 of those tests were conducted to produce and study the heaviest radioactive isotopes possible. Now, those tests are not true analogs of the astrophysical R process because the R process itself probably operates over longer time scales, still brief and rapid, but longer time scales and at higher temperatures. So you get some information, but it is limited. And that testing program was ended in 1992. We do, of course, have an example of an R process event that was caught in the act, the well-known 2017 merger of a pair of neutron stars, one we saw a simulation of a few minutes ago. That event took place in the outskirts of a galaxy located 40 megaparsecs away. And then you make the association between the R process and the kilonova by comparing the colors and the decay timescales with the expected opacities of radiation as it passes through millions of transitions of freshly produced heavy elements, often thought to be dominated by the lanthanide elements. And in general, it is not possible to detect individual elements, much less derive precise abundances, because the ejecta velocities are so high in kilonovae. So the ejecta in just that 2017 event were moving at somewhere between 10 and 30% of the speed of light. And you can see the consequence of that in the figure on the right here, which shows what happens to the predicted flux distribution as the velocity increases from the top one to the bottom one. So fast or relatively slow to fast and faster as you go down. And what you see is that any lines that are present in that spectrum that are produced by the elements in the ejecta itself, those lines just get blurred together as the velocity is increased. There have been a few potential detections of freshly produced R process elements in the spectra of that event, and the figures here show a few of those. The one on the left, the figure on the left, shows a potential detection of strontium in that remnant. The one on the bottom shows yttrium, and the one on the right shows tellurium. And within each of the top two panels here, you can see the time evolution of that spectrum over the course of several days. The vertical dashed lines here, I think, yeah, they're all vertical dashed lines, mark the wavelengths of the absorption transition wavelengths, and then the shaded regions that evolve with time show how that line might impact the spectrum of the kilonova event. Now, of course, modeling the opacities in these events, because you're dealing with many millions of transitions of at least a few tens of elements, that's really complicated. And there are several groups that are working on this problem. And it's work that's been ongoing for a couple decades now and will continue to be ongoing, I'm sure. I'm not involved in that work, but I think it's a really promising route forward. And you need to be doing that work in order to correctly interpret the information that you're getting from the spectra of kilonova. And even if you just take away the lines here and just look at the spectra themselves, clearly there's information there. So I think this is going to be an exciting route forward going in the decades ahead. But even so, the detailed element by element composition of that ejecta is not known experimentally. So all that platinum and gold that you kept hearing about in the press releases and the news coverage, it's all inferred. It's not observed directly. But the UV spectra of stars like the ones that you see here are the only places you can actually detect elements like platinum and gold. And to the best of my knowledge, there are a total of 7 detections of gold. The figures here show 6 of them, and then the seventh one just didn't publish a figure. Now, of course, there's nothing magical about the UV, but it has some key benefits when you combine it with optical and near infrared spectra. So first, UV has just many more lines. So you get better statistical uncertainties in your abundances, and you can better cross-check your blind detections, your identifications. Do I have this line right? Do I know what this element is? Do I know what's causing this absorption? Having multiple lines, including some in the UV, can really help give you some confidence that you have actually detected the element that you think you have. The next thing the UV does for you is that it gives you a much wider range of electronic transition properties that you can use to better constrain the way you're modeling the stellar atmosphere. So I'm thinking here in terms of going from a 1D to a 3D hydrodynamical model, or going from the standard LTE radiative transfer assumption to non-LTE models, either for the radiative transfer itself or for the model atmosphere. The UV just gives you many more lines and many more different lines from different levels that you can use to constrain those models. And then finally, you get just many more elements altogether. So more elements gives you the ability to, do new and interesting physics together. Things that are undetectable typically in optical or near infrared spectra. So here are some examples. We can detect lots of R process elements in optical and UV spectra of well-selected R process enhanced stars. So an R process enhanced star is exactly what it sounds like. A star that has a large enhancement of R process elements relative to the overall level of metals in the star. So the figures that you're looking at here show pieces in particular of the ultraviolet spectrum around some lines of R process elements, ranging from relatively light R process elements near the middle of the periodic table, so like selenium, element 34 in the upper left, all the way through to gold, element 79. And we've been able to detect elements as heavy as thorium in this star. That's element 90. In other stars, we've been able to detect uranium as well, element 92. So many of the elements that you see highlighted here, all right, I've chosen these particular pieces of spectra for a reason. The ones you see highlighted here have only been detected in a very small number of stars. Sometimes that number of stars is like one or two, and maybe in a better case scenario, it's like 10. But compare that to the number of elements that you tend to think of coming from large astronomical surveys doing stellar abundance work, right? Where you get hundreds of thousands, or in the case of, sort of bulk compositions, metallicities, maybe carbon abundances, or think alpha elements, maybe a few million stars. So even in a case for the elements that I'm showing you here, where you only have a handful of detections, even that has taken the result of sustained efforts by many people across decades. Not just me, and not even just my team. Many people, many groups around the world for decades. But when you put all of that together, this is the rich periodic table that you get. So this particular star has what's perhaps the best known chemical inventory of any object beyond the solar system. So 65 elements have been detected in this one star. Now it's relatively easy to collect optical spectra. You can do that using a number of ground-based telescopes, but UV radiation, of course, is blocked from the surface of the Earth by Earth's atmosphere. That's great. We don't get sunburns as intensely that way. But high-resolution UV spectra can only be collected right now with one facility, the Hubble Space Telescope. So the challenge is there's only one facility, and it's highly oversubscribed. But the upshot is that UV spectra give you a 50% increase in the number of elements you can detect in cool stars. So in terms of the R process, we were able to detect 42 R process elements in one star that likely formed from the remnants of a single R process event that occurred early in the history of the universe. And the key advance here was having access to that UV spectrum from Hubble. So the figure shows what we call the abundance pattern. So that's on the vertical axis, log of the abundance versus atomic number on the horizontal axis. The black dots mark the abundances in the star, and the star is HD 222925. And let's spend the next couple minutes looking at some of the more interesting features of this abundance pattern. So the elements that are shown here in the yellow boxes are the ones that required UV spectra. The red line, which is shown for comparison, it's not a fit, it's shown for comparison. That marks our best inference of what the R process contribution to the solar system has been. Now, it's not that there's been an R process event in the solar system, but some of the elements that were produced by R process events before the formation of the solar system got incorporated into the solar nebula. And then the bulk composition of that solar nebula is thought to be retained in particular classes of meteorites, the CI type carbonaceous meteorites. So you can actually go through and count the atoms in your mass spectrometer. And then from that, you can model, you can infer, you can back out what the R process contribution to the solar system has been. So that's the red line. And then if you compare the stellar and the solar patterns for the heaviest R process elements, the ones on the right-hand side, there is a remarkably good match between them. But that agreement does not seem to extend to the lighter R process elements. And it's not that I think that either pattern here is necessarily incorrect. I think they're just probing different things. The solar pattern reflects the integrated average yields of many R process events over the course of, I don't know, 8 gigayears of cosmic time, while the stellar pattern, the dots, reflect the outcome of a single R process event. So we now have a reasonably complete R process abundance pattern derived from this star. And what do you do with that? Well, I think there's a lot of opportunities to learn new astrophysics between here by comparing the stellar pattern and model. So if you have a favorite model for some R process event that occurred in a kilonova or in some rare kind of supernova that might be able to host the R process, this star, the black dots here, give you a new template independent of the solar pattern that you can use to compare against. We can also use this star to guide our interpretation of the abundance patterns that we find in other stars, in particular, other R process enhanced stars. HD 222925 is not the first R process enhanced star that we found. Other teams, many teams around the world have been doing this kind of work for, geez, more than 30 years now. And depending on how you count, there are somewhere between several dozen and several hundred R process enhanced stars that are known. But because this particular star has such a complete chemical inventory of R process elements, let's try to use that to help interpret the patterns that we find in some of those other stars. And we'll do that today in the context of the heaviest elements that you can produce in nature. So the R process almost certainly produces elements heavier than uranium. And we will call these elements transuranic elements. These are the ones that are highlighted on the periodic table here with the orange boxes. They're all radioactive, in many cases highly radioactive, and they decayed a long time ago into other isotopes. And so that is the fundamental reason that we don't observe transuranic isotopes in the cosmos today or in any measurable quantities here on Earth. They decayed long ago into other things. One of the major decay channels is fission. So that fission process will produce two lighter nuclei. It produces a handful of neutrons and then some energy in the form of gamma rays. Those two lighter nuclei will decay, mostly through beta decays, back towards stability, and they will populate elements listed near the middle of the periodic table. There are a lot of open questions related to transuranic elements. What is the distribution of transuranic nuclei that you can produce in an R process event? What are the heaviest nuclei that you can produce in an R process event? Can you go as far as heavy as the super heavy elements? How reliable are the extrapolations that are used in the model predictions on the nuclear physics side? Everything here is an extrapolation when you get to these transuranic isotopes, with a very few exceptions. How reliable are those extrapolations? And then there are other big open questions related to the transuranic nuclei fragments themselves. What is that distribution of transuranic nuclei fragments? These are some of the questions we'd like to be able to address. Okay, so the figure on the left here shows the distribution in mass of fission fragments for 3 transuranic isotopes. These are experimental from the laboratory physicists, and for the purposes of this talk, you can just ignore all of those different color lines, just focus on the black dots. So that's the figure on the left, the experimental ones. On the right, you have some theoretical predictions for the fission fragment distributions for other isotopes, other transuranic isotopes. And the different lines there on the right simply reflect the predictions for what the distributions look like if you change one of the parameters in your model. In this case, it's a parameter that governs the process of how the nucleus splits into 2. So both the theory on the right and the experiments on the left here point to a common theme. The probabilistic nature of fission leads to dozens of combinations of lighter mass nuclei. So the key point to notice is that the fission fragments exhibit a bimodal distribution. There's a lighter peak and a heavier peak in mass. So there is this critical need for experimental constraints on the fission fragment distributions if we want to answer some of these big questions. So I will show you in just a minute here some abundance signatures in stars that suggest that some of the elements listed near the middle of the periodic table can originate in part as fission fragments of transuranic nuclei. So what did we do? We performed a meta-analysis of the abundance patterns of 42 R process enhanced stars in the Milky Way. This is all literature data. There's nothing new here. We're just interpreting it anew through the lens of that star with a remarkably complete R process abundance pattern. And the figure here shows how we're going to illustrate the results. It's a little bit strange, so let's talk this through. The vertical axis shows the shows the abundance ratio of various pairs of R process elements. And then the horizontal axis shows the europium to iron ratio, which we're going to use as a proxy for the overall strength of the R process that enriched each of the stars that we're going to include in the sample. So every dot that you'll see will represent one measured pair in one R process enhanced star. And if there is a flat trend in this diagram, that means that the elements are being co-produced in the R process. In other words, the production does not depend on the overall strength of the R process. If there is a statistically significant positive slope, that tells us that one element is being produced more than the other one as the strength of the R process increases. So here are our results. I've separated them into 5 different panels, ordered by increasing atomic number. So the pairs of elements in panels A, C, and D exhibit no significant positive slopes. And that indicates that they are being co-produced, those elements are being co-produced in the R process. And then the pairs of elements in panels B and E exhibit non-zero positive slopes, so they're correlated with each other and with the strength of the R process. So one characteristic of a stronger R process might be greater production of the heaviest nuclei, transuranic nuclei, and therefore potentially greater production of their fission fragments. So we associate the elements in panel B with the lighter fission fragments. So this is ruthenium, rhodium, palladium, and silver, elements 44 through 47. And the elements in panel E we associate with the heavier fission fragments and elements that just naturally require a stronger R process for their production in the first place. And the diagram in the lower left here just shows where these elements are in mass number. We are not aware of any other nucleosynthesis process that can reproduce this observed behavior. So there are a few potentially interesting implications of this finding. So first, these signatures are observed in a fair fraction of metal-poor stars, indicating that R process events that are capable of producing transuranic nuclei, they also must have been relatively common in the early universe. Next, you can infer the mass of the fissioning transuranic nuclei by simply adding up the mass numbers of the fragments. And if you do that, you find that masses greater than 260 are required. So A is the sum of neutrons and protons in the nucleus, greater than 260. That's what's required here. Now, that mass is not quite yet in the range where the nuclear physicists propose an existence of some island of stability, somewhere in the neighborhood of 290 or 300. But it does leave open that possibility. And one thing I actually think is quite interesting here is that this mass is greater than the mass of any of the confirmed transuranic nuclei that have been isolated in the debris from those nuclear weapons tests that were conducted here on Earth. So maybe it's not surprising, but it's good to see it maybe confirmed that cosmic R process events might be more extreme than our terrestrial tests. And finally, I think this might boost the prospects for finding and searching for transuranic elements in the kilonova aftermath of neutron star mergers, at least ones that would occur in the future. So the luminosity of a kilonova, as we've said, is powered by radioactivity as the energy released during all those decays diffuses out of the ejecta. The lower set of curves here show the light curve, so brightness versus time, if that ejecta does not contain californium-254, which is a relatively long-lived transuranic isotope. And the upper set of curves show the predictions what happens if you include transuranic isotopes and californium-254 in your model. And that gray band shows that that upper set of curves might be detectable by JWST on a timescale not of days, but of months after a merger. And detecting these signatures, I think, would represent a significant achievement for multi-messenger astrophysics, right? There's so much modeling that goes into that. And it would also be a nice confirmation of the picture that we see in old stars. Okay, so I'd like to, for the last part of the talk, leave the R process behind. The cosmic dark ages ended with the formation of the first stars. These stars are also known as POP3 stars, and they formed from the primordial hydrogen and helium and trace of lithium left behind after the Big Bang, just a few 100 million years after the Big Bang. And the simulation that we're watching here shows the radiation that's being emitted by those POP3 stars as their proto-galaxy is forming. So the first stars would have produced the first metals. They produced the first ionizing radiation after the cosmic dark ages, and they might have left behind the first stellar mass black holes. These first stars are predicted to have been quite massive, characteristic masses somewhere greater than 10 solar masses, and they probably would have been very short-lived for that reason. No metal-free POP3 stars have been found yet. So that raises the question, what were the first stars like? And observing the first stars and their chemical descendants is a major scientific priority for the decade ahead, or decades ahead, really. Um, Virtually every major astronomical survey for the next decade that includes a stellar component lists the first stars as one of the key scientific priorities. And most major telescope facilities do the same. And what I like about this is that there's such a wide range of methodological approaches to understanding the first stars by all of these different surveys and telescopes. There's everything here from gravitationally lensed, high redshift objects to the shape of the 21 centimeter power spectrum, absorption lines and damped Lyman alpha systems to high redshift, and to bring this back home, even low metallicity stars, old stars in our own Milky Way and local group. So while I'm here to promote, among other things, the virtues of UV spectroscopy, let's focus on ways that a couple of these future missions, and one in particular, the Habitable Worlds Observatory, how that could revolutionize our understanding of the first stars. Now, the Habitable Worlds Observatory is still in its design stages. The technology development here is being led by NASA's Great Observatories Technology Maturation Program, and the goal is to have a 6-meter aperture UV optical near IR telescope with a coronagraph to launch in the early 2040s. So the design, the exact instrumentation on habitable worlds have not yet been set. The instrument teams, the design teams, the engineering teams, the science teams, the management teams with the budget, we're all still going back and forth. And look, the name, the top line science case, right? Habitable worlds, which is so cool, I think. But let's not kid ourselves. This mission would be transformational for every area of astrophysics, including the first stars. So what I'd like to do now is briefly show you 3 ways that habitable worlds could revolutionize our understanding of the first stars. First, you get a sensitivity gain of somewhere between 100 and 1,000 times relative to what you can do today with STIS or COS on Hubble. That's a gain of 5 to 7 magnitudes in the UV. And that means you actually get to choose scientifically interesting targets to study, not just stars that happen to be bright and also happen to be scientifically interesting. You get to choose. And the figure on the left shows the parameter space that gets opened with this. It's the apparent magnitude versus the metallicities of confirmed known metal poor stars. And habitable worlds pushes you into a regime where virtually all of the known F and G type metal poor stars that they can be observed in the UV. And the diagram on the right-hand side, just a little schematic showing where in the Milky Way you could observe those stars with habitable worlds. And I like to sum up this advancement this way. With habitable worlds, you could obtain a UV spectrum of comparable resolving power and signal to noise to the optical spectrum for any star you could observe from the ground today. Next, that UV spectrum gives you access to many, many more lines than the optical or the near IR spectrum does. So more lines, better lines, more species, and more elements. And this diagram illustrates some of the stronger lines here. The periodic tables that I've put there at the bottom illustrate which elements are detectable in the UV and the optical spectrum of a sort of a typical G-type star with a composition typical of one of these second generation stars that we've identified, or not me personally, but that we as a community have identified in our Milky Way. So the optical alone gives you 10 elements, more or less. And the UV spectrum below the Balmer jump gives you about 19 elements. There's a little bit of overlap in the elements there, but put them together and you get 23 elements. And let's remind ourselves what those 23 elements represent. Those are the metals produced by probably one POP3 supernova. The more elements you have, the better constraints you get on an individual POP3 supernova that occurred in our Milky Way. And finally, that UV spectrum gives you the ability to detect elements when their abundances are far, far lower than what you could detect from the optical lines alone. And for some elements, including the ones that I'm showing you here, so that's silicon, carbon, iron, and magnesium, for those elements, the UV lines are just much intrinsically stronger at the conditions that you typically find in late-type stellar atmospheres. Most of these lines originate with electrons in the dominant population reservoirs, again, at the conditions typically found in late-type metal-poor stellar atmospheres. And those detection thresholds, as you can see by the model curves here in the different colors, those are somewhere between 1.5 and 4 decks, 1.5 and 4 orders of magnitude lower in number density or abundance than what you can get from typical optical lines of these elements in sort of a similar kind of star. So here's another way you can say this. If you find a candidate metal-free star that has survived from the early universe, going to the UV is a way to demonstrate that there really, truly are no metals present in that star. So those are the advances with habitable worlds. I have one slide here showing what the extremely large telescope, what the ELT could do with ANDES, the high resolution, mostly optical IR and a little bit of UV spectrograph that's being designed for the ELT. Now, ANDES does not go quite as far into the blue or the UV as habitable worlds does, but what it gives you is this enormous collecting area of the primary mirror. That has the ability to revolutionize our understanding of the first stars because it pushes observations deep into the galactic center or deep into the halo of our Milky Way and the dwarf galaxies surrounding the Milky Way in the local group. And these are the sites, the center, the galactic center, and those dwarf galaxies where the first stars are predicted to have been born and where their second generation chemical descendants are likely to be found today. So the science case documents for ANDES are all published now. You can see the list here. And the ELT and ANDES would be revolutionary for our understanding of the first stars. So I am super excited about the possibility of using ANDES and habitable worlds to study the first stars and, of course, all of the elements across the periodic table. I think the future for studying the origin of the elements across the periodic table is bright, especially in the UV. And I look forward to pursuing these ideas alongside you in the decades ahead. Thank you for your attention. Thank you for putting up with this on Zoom, and I look forward to hearing from your questions.
Thank you, Ian. It was an extremely interesting talk and certainly inspiring. I think we are all convinced that we need the UV. So there is time for questions. So please feel free to speak up directly to our speaker, or if you want to write in the chat some questions, I can translate it to him. Any questions from the audience?
Hi.
Hello.
Yes,
Hi.
Richie.
I'm the doctoral student of David and Close. Yeah. So I'm also working on our process, and I learned a lot from your talk and also many things beyond our process. Yeah. I have a question about your slides about the five region. You're comparing the metallicity abundances ratios with the European abundances. Yeah, I'm wondering that why you use zirconium and barium for the light elements and heavy elements, but you do not use the other elements such as for heavy elements. Why don't you use europium but use barium? I have this question.
Yes. Thank you for that question. I actually look forward to chatting with you this week too. So at some level, this is a matter of practicality. Barium and zirconium were chosen because they are relatively well measured, both in terms of they are frequently measured, so they're available in most of these stars, or all of these stars, actually. That was one of the requirements for inclusion in the sample. And because they have multiple lines, so you have typically multiple good lines to use for the analysis, so that the abundances themselves are considered to be reliable. Europium, of course, is also reliable, and we just didn't choose it for that case because we wanted um, something at the lighter end of the lanthanide elements, just to watch sort of how the behavior changes as you go from the light end of the lanthanides to the heavy end. You certainly could reproduce the analysis using a different set of reference elements, and you would find the similar results.
Okay, thank you. And I want to ask further about the for example, you use the zirconium barium, and it can be also produced by our process. And I think the sample has not a very narrow metallicity range, so some of them might be affected by more as the process, and some are less. So can this affect the slope of the figure or not?
Yes. So, part of what we're trying to do here is use the statistical power of a larger sample. I mean, larger in this context is still just 42, right?
Yeah.
We're not at on the order of millions here. Um, but putting all of these stars together at one, so that variations like what you're describing, where you have maybe a few events, or ideally one event dominates the pattern, the enrichment of a particular star. But maybe it's only an 80-20 domination. It's not 99 and 1. So we'd like to try and wash out, marginalize over some of those signatures. And that's ideally the power of having the statistics here. When typically these are published one star at a time or two stars at a time, and so you don't have that ability to sort of cross-correlate and look for this kind of behavior. It's only when you do the meta-analysis that you can do that. So of course, yes, there are ways one could improve this. Ideally, you'd want to maybe even select a more pure sample potentially, but then you risk losing that statistical power.
Okay, thank you. Looking forward to talking to you in person in the following days.
Yes, likewise.
Thank you.
More questions?
Yeah, I have a question. Hi, Ian. It's Mike Beasley here. I'm a member of staff at the IC. I enjoyed your talk
Thank you.
very much. It was super interesting. So I had a question. So you're hopefully in the future we're going to get all this wonderful UV data. I was wondering, where are the models, the stellar atmospheres, the opacities? I mean, is there a lot of work that needs to be done to be able to interpret these data that's upcoming? I mean, what are the key challenges there, do you see?
Yes, excellent question. At present, the models are you just sort of think standard Marx model atmospheres, for example. Those should include all of the relevant sources of opacity. When you get down into the UV below the atmospheric cutoff, typically when you're looking at metal-rich stars, solar-type stars, the opacity becomes a mess, right? There's been historically this challenge of identifying the missing opacity in the sun, for example. I know Carlos has worked on that a bit himself. Um, and that certainly would complicate the analysis. When you get to extremely metal poor stars, the some of the dominant sources of opacity being the metals, that becomes a much more simple calculation, and it really starts to revert back to this hydrogen as in some form of hydrogen bound free, as one of the major sources of opacity. So there is certainly work to be done here in demonstrating that the model atmospheres are reliable for these extremely metal poor stars. The challenge is that there's just not that much observational data to use as a constraint yet. So one of the things I'm trying to do is develop some of those samples now so that we can develop those tools and do those checks in the next decade before Habitable Worlds launches. But you're absolutely right to ask the question. I think the concern is not so much what is the missing opacity. I think that will not be an issue, but just demonstrating that we actually know how to do this. And if we find cases or find that we don't have the necessary, if we're not able to reproduce the observed, say, flux distributions, that gives us time to pursue those new calculations of whatever that might be. In terms of scattering or something like that. Yeah.
Okay. Thank you. Thanks.
You're welcome.
Carlos?
Following up with the same topic, I wanted to ask you about the status of the availability of the atomic data for these heavy elements, values, damping constants, all of that.
Yeah. So for the heavy elements, I'm assuming you mean the R process elements. For most of the dominant transitions, basically anything you'd find in typical metal poor stars, R process enhanced stars. For most of the lanthanides and elements heavier than that, the atomic data are generally pretty good. And a large part of that, particularly for the lanthanides, you can owe to sort of just sustained excellence over the course of decades, just persistence by the atomic physics community over decades when they've been dramatically underfunded, just making do with archival spectra and finding new ways to use old FTS spectra to derive new level energies and transition probabilities, branching fractions, all of that fun stuff. So the transition probabilities are generally in pretty good shape for the astrophysically interesting transitions. Damping constants, a little bit less so, but in most cases, the lines of interest are not saturated. A few of them, sometimes they are. Mostly you're dealing with weak lines, weak on the curve of growth, kind of weak. And so it's less critical. The bigger challenges come for the lighter elements where we just don't, I mean, the atomic data exist, and often, again, we're dealing with dominant transitions. We just don't necessarily have a lot of cross checks that we can do to astrophysically verify that they give reliable abundances yet. And to answer a different question that you didn't quite ask, we're in desperate need of a lot of non-LTE calculations for many of these elements as well. Just about everything I've shown you here today is an LTE calculation because that's what's available. There is interest that's growing, and there are teams that are working on this. I think I saw someone on the call here who may have been involved in some of that work. But that's another point where sustained effort needs to be invested over the next decade.
And the collisional data, for example, for hydrogen collisions, for doing the non-LTE, all that exists, all the radiative, the bound-free.
Correct.
Section. Okay.
Yes.
More questions? Maybe a last one? Maybe I can ask something to Ian. So first of all, I found quite interesting that in the optical, the last metallicity indicator we lose is the calcium H and K resonances, while in the UV you have magnesium, which is apparently a stronger indicator of metallicity. Is that correct?
That's correct.
That's very cool. I do remember, related to these UV emissions, something called CITUS. And do you know if it's something that is going to happen? Because we clearly need more, UV instruments on Earth, on space. So is there any prospect on some extra missions could be launched?
Yeah. So CETUS, the one you're referencing, was not selected for further development by NASA. I want to say 6 or 7 years ago, but there are a couple that are coming. One is called Castor. That's a Canadian mission. Generally, these are photometric, so they have some UV photometric bands and some optical as well. The other one is UVEX. It's another. That's a NASA. I think that's a mid X1. So I think that's the half a billion US dollar category. I might have that wrong, but the UVEX mission is still moving forward, I believe. that would be a modest size mirror, but entirely UV. And so neither of these give you high resolution, high spectral resolving power in the UV, but they do give you some low resolving power across the UV domain, and some optical as well. So those, last I checked, we're still on schedule for launch in 2030, 2032, somewhere in that neighborhood. So that would be a bridge potentially from Hubble through the 2030s and into the 2040s, where, fingers crossed, habitable worlds can pick up the mission again. So I'm excited about those, even if they are just low resolving power. The lines we're talking about here are lines you could see in low resolving power as well.
Okay. Thank you so much. I think it is time to wrap up here. Before thank Ian again, let me just let you know that if possible, due to the weather and the alarm, we will try to meet Ian tomorrow morning at the AC in Omega's room at 9:30. So if any of you are interested and reach him, so we will be meeting, and then during the morning you can also contact him. So thank you, Ian, again for this super, amazing talk. See you soon.
Thank you all.
Thanks.
Okay, I have